Returning to the description of radiation, we next come to gamma rays and X-rays. Gamma rays are electromagnetic radiation, as are radio waves, microwaves, light, and X-rays. The big difference is that gamma rays are much, much more energetic than light, about 1,000,000 times. We see here that X-rays are lower energy than gammas, and that's almost always true. But the real difference is not their energy, but where these photons originate. Gamma rays are emitted from the nucleus, and X-rays come from the atomic electrons orbiting the nucleus. Given that nuclear energies are thousands to millions of times bigger than atomic forces, it's no wonder they are more energetic. X-rays almost always appear during nuclear decay also. There is still more to learn by looking at the Tritium Equation. When tritium decays, it goes from a hydrogen atom with one lonely electron to a helium atom with only one electron. However, helium needs 2 electrons to be neutral, thank you very much, so the electron falls into the new helium orbital, releasing an X-ray. When another electron is eventually captured, another X-ray is emitted. This is one way to get X-rays. Your dentist, when she X-rays your mouth, uses another trick to get X-rays. But again, we'll wait another day to explain bremsstrahlung. Gamma rays can be admitted as the only radiation after a decay, but this is uncommon. Usually gammas are emitted along with alpha, beta plus, and beta minus decay. Now that we're done with the naming of the parts, let's look a bit closer at the different types of radiation and their characteristics. Alpha and beta radiation are particulate radiations and are directly ionizing. They lose their kinetic energy by interaction of their charge with the charge of the atoms in the media that they are traversing, meaning that the combination of their kinetic energy and charge, they are able to knock electrons off of atoms of the stuff they're going through. Both alpha and beta particles have ranges, that is, there are distances that they travel, the range, and then they are completely stopped. These ranges depend mostly on the type of particle, whether it's an alpha or a beta, the kinetic energy of the particle, and the density of the medium. Alpha particles are the Tyrannosaurus rex of nuclear radiation. They are huge, they are highly ionized, and they beat up whatever they go through. Because alphas are so highly ionizing, they lose their kinetic energy very quickly. Even alpha particles with 7 or 8 MeV of kinetic energy only travel a few centimeters in air. Let's look at an alpha track in the cloud chamber. Note the scale at the bottom of the figure. The length of the line is 1 millimeter. There is a central core that is highly ionized, and every now and then there is a large knock-on collision that creates a delta ray, carrying energy away from the central core. For low Z materials, about half the energy is deposited in the central core, and about half is deposited by delta rays. Beta particles or electrons are anti-electrons that are ejected from the nucleus. Beta rays are much less densely ionizing than alpha particles, and therefore their range is greater than for alpha particles if they have the same energy. The range of a beta particle in air is about 4 meters per MeV of kinetic energy. Let's look at an electron track in a cloud chamber. Notice the scale at the bottom of the figure. The length of the line is now 1 centimeter. We see here during the high energy part of its travel, the electron often travels more or less in a straight line. But near the end of the track, when its kinetic energy is low, it's bounced around much more and loses much more energy per unit travel. The next figure is a cloud chamber track of a low kinetic energy or electron, or if you will, the track of a high energy electron near the end of its range, where it's lost most of its kinetic energy. Positrons have the same track structure as beta minus particles, but at the end of the positron track, it reacts with an electron in the stopping media and both the positron and this electron are annihilated, producing two 511 keV gamma rays. Speaking of gammas, unlike alpha and beta rays, gamma rays are not directly ionizing, but rather they interact with the electrons in the media and give them energy. Because of this, the ionization density is much like a beta ray. The big difference is gamma rays have no range. They go on forever. They do have half-value layers, however. By using shielding, we can lower the dose from gammas to whatever level we want, except 0. A half-value layer is the thickness of a given material that lowers the dose from gamma rays to half its original value. Guess what two half-value layers do? In math, D equals D naught e to the minus mu x, where D is the gamma dose exiting the shield, D naught is the dose from the gammas as it enters the shield, mu is a characteristic of the shielding material, and x is the shield thickness. There's a reason this looks very much like the half-life decay equations. Finally, neutrons are also indirectly ionizing radiation. They are neutral, they don't interact with the electrons at all. Their only interactions are when they splat into the nucleus.